Okay, hello everybody. Good morning, all of you. So we'll start with our quote. And today's quote is, you can't go back and change the beginning, but you can start where you are and change the ending. Okay, past is not in our hands. There is no point in regretting about it and worrying about it because we cannot change it. But if you can change the present, you can change the future. So now you can start, and based on how you do it, you can change the ending. And today is the birthday of, I think, all are most familiar about this particular actor, Sushant Singh Rajput. Recently, we lost him. But within short period, he became very popular and famous and loving. And Sushant Singh Rajput is an Indian film actor, dancer, television personality, an entrepreneur, and a philanthropist. He has done a lot of social service also, though he is very young. And Rajput started his career with television serials. He gave an award-winning performance in GTV's popular soap opera Pavitra Rishta in 2009-11. And Rajput made his film debut in the buddy drama Kai Poche in 2013, for which he received nomination for the Filmfare Award for Best Male Debut. And his highest grossing releases came with a supporting role in the satire PK, followed by the title role in the sports biopic MS Dhoni. The Untold Story, MS Dhoni, The Untold Story in 2016. For this performance in the latter, he received his first nomination in the Filmfare Award for Best Actor. And apart from acting and running ventures, Rajput is actively involved in various programs like Sushant for Education as a part of efforts to help young students. And he appeared on Forbes India's Celebrity 100 list twice since 2017. Okay, so but unfortunately, we lost him at very young age. Okay, today we discuss about the performance of gas turbines. And before going to that, okay, what have you tried those problems? Nobody is responding. No time.
No, sir.
You didn't try?
No, sir.
Okay, because if you leave it like that, I will proceed and I will go further, and later you may be left with doubts. Anyhow, it is completely self-explanatory. Okay, quickly we will see what the problems are. Okay, here, this is the problem number 2, which is twin shaft turbines. So we are given the compressor pressure ratio, turbine inlet temperature. So these are the main two things, and also ambient conditions, PATA. Okay, these are given. And what else we want all the parameters like compressor efficiency. There are two turbines, so isentropic efficiency of each turbine is given, and mechanical efficiency of each shaft, that is compressor shaft and power shaft, and combustion efficiency and combustion chamber pressure loss and exhaust pressure loss. Same way, all the data will be similar. Only thing is the configuration is different. Okay, so if you see, this is the configuration, and 1, 2, 3, 4, 5. And so if you draw, already the graph is drawn, the last class. So it will be like this. So not 1, not 2 dash, not 2, not 3, not 4 dash, not 4. This is ideal, and this is actual for the second turbine. Okay, this is the way we have to draw the TS diagram. Okay, so this is turbine 1, this is turbine 2. Okay, so turbine 1 runs the compressor. That's why WT1 is equal to WC by mechanical efficiency. And the power will be equal to M dot A WT2 mechanical efficiency. Okay, so this is the way it will be. And only thing is, as I told, I have to get the pressure ratio here based on how much work that is needed. That is, from this, I can write this as CPG. WT1 is CPG into T03 minus T04 is equal to WC is CPA into T02 minus T01 by mechanical efficiency. Okay, so in this, the unknown will be T04. So once I know T03 and T04, T04 dash is to be obtained from the turbine efficiency. So eta T equal to T03 minus T04 by T03 minus T04 dash, which gives me T04 dash. Because T04 is obtained, T04 dash is to, why T04 dash? Because I want pressure. Okay, so P04 by P03 is equal to T04 dash by T03 to the power of gamma G by gamma G minus 1, which will give me P04. This way I have to get P04 because I want the pressure ratio for the second turbine. So P04 is obtained like this. And the P05 will be equal to P01 plus delta P exhaust losses. Okay, so here there will be some loss. So it will be more than that. So once I know P04 and P05, I know the pressure ratio of the second turbine. Okay, so once I know these pressures, I can find out this temperature, and using the turbine efficiency, I can find out this temperature. Then WT2 will be equal to CPG into T04 minus T05. Okay, this is the way I have to go about it, and the power will be obtained like this. Okay, just we will see those steps of calculations. So T02 minus T01, we can get it from this formula, T01 by efficiency C, r to the power of gamma minus 1 by gamma minus 1. So I get this. And WTC, Cp into this delta T by mechanical efficiency will give me first turbine work, WTC. And P02 is, this is actually wrong, P03 it is. Okay, that is P02, which is 12 bar, into 1 minus the losses 0.06, that is 11.28 bar. Okay, then the turbine work CPG T03 minus T04 is WTC. So from this I can find out T03 minus T04, which gives me T04. And then I have to get the pressure ratio. Direct the formula he has used to get the T04 dash. And so that is the way. Okay, all these steps, the same thing, whatever I have explained. You can just go through it. Okay, and reheat cycle with polytropic efficiency. So here, again, compressor pressure ratio and polytropic efficiency of compressor and turbine are given, and turbine inlet temperature for both turbines. Okay, so that is reheated to the same 1525 Kelvin. And pressure loss in the first combustion chamber, pressure loss in the second combustion chamber is given. Okay, it is directly given 0.02 bar, 0.03 bar, so you can use it. And exhaust losses 1.02 bar. Okay, so that is the turbine, second turbine exit pressure will be equal to ambient pressure 1.01 plus 1.02. So it will be 2.03 bar. Okay, so this is the way the configuration is. So we have seen that it will be like this. So first combustion pressure loss will be here, and second combustion pressure loss will be here, and exhaust loss will be here, and this will be not 1, not 2 dash, not 2, not 3, not 4 dash, not 4, not 5, not 6 dash, not 6, like this. Okay, this is the way I have to go about it. So here WC will be CPA into T02 minus T01, and WT will be WT1 plus W22, which is CPG into T03 minus T04 plus T05 minus T06, and QH will be CPG into T03 minus T02 plus, in the reheater, T05 minus T04. It will be like this. Is it okay?
Yes, sir.
And these two temperatures are same. So that is the way we have to go about. And first, because polytropic efficiencies are given, so I have to find out the n minus 1 by n for the compressor, n minus 1 by n for the turbine. So gamma A minus, this is gamma A minus 1 by gamma A. This is gamma G minus 1 by gamma G. Okay. So, and T02 by T1 is P02 by P01 to the power of n minus 1 by n. This 0.3210 I have to keep. So that is the way. The remaining thing will be as it is. The procedure will not be different. Okay, you can go through those problems. Okay, now we discuss about performance characteristics of gas turbines. Actually, these are important things, and most of it is self-explanatory, the graphs. So if you draw graphs between net output and efficiency, or SFC, instead of efficiency, SFC is taken. And so here you will get net output, and here we take SFC. Okay, SFC, what is the difference between SFC and efficiency? How they are related? They are proportional to each other or inversely proportional to each other? If one increase, other increase or decrease?
Inversely, sir.
Inversely, right? If efficiency increases, actually fuel consumption decrease, SFC decrease. If efficiency is less, more fuel consumption or more specific fuel consumption will be there. So they are inversely related. So that we have to remember. And so the parameters are, we know that pressure ratio is one parameter and T03 is one parameter. These are the main parameters. So as I told, if you draw graphs, the R represents a C and T03 represents T. Okay, so we have drawn the graphs for C and T. Instead of C and T, actual values are pressure ratio and the maximum temperature, turbine inlet temperature. Okay, so if you draw graphs, the graphs are drawn for simple cycle and heat exchange cycle. Okay, so the main difference you can see that in simple cycle, the efficiency and pressure ratio, how they are related? As pressure ratio increase, efficiency increases.
Increase.
It will increase it.
Okay, and output
Increases.
no. There is optimum pressure ratio, right? Means there will be increase and decrease, isn't it? Do you remember? We have drawn the net output versus pressure ratio. It increases and decreases like this, isn't it?
Yes, sir. Yes, sir.
So there is an optimum pressure ratio. It increase and decrease. With respect to pressure ratio, efficiency continuously increase and output increase and decrease. And coming to T03, okay, if turbine inlet temperature increases, what happens to output?
Output will increase it.
output will increase, right? So that's why I want
Yes,
to have the maximum temperature possible, which is restricted by metallurgical limit.
yes, sir.
And what happens to efficiency?
Efficiency, we cannot say, sir.
Hmm?
Efficiency increases, sir, if you increase the inlet temperature.
If the inlet temperature increase, efficiency increase, output increases and efficiency also increase. Okay. And so we will see how the graphs come. Okay, this is the way the graphs will be. Okay, so these are drawn for different as this is for 1100 Kelvin, this is 1200 Kelvin, this is 1300 Kelvin, this is 1400 Kelvin, this is 1500 Kelvin. Okay, the variation of SFC and output are like this. And coming to pressure ratio, as for a given pressure ratio, R is equal to 6, it will be like this. R equal to 8, it is like this. R is equal to 10, like this, like this. So these are the family of curves. Now you can see whether our prediction is going right or not. So if pressure ratio increase, what is happening to SFC?
It will increase, sir.
You see this pressure ratio 6, 8, 10, 12, like that. What is happening to SFC?
Decreases.
Decreases. Why?
Increase.
Because efficiency increase, isn't it? As pressure ratio increase, efficiency increase, so SFC decrease. So it is decreasing very much like this. Am I clear? And output, as R increase, output you can see that there is an increase here and there is a decrease here. This is output. Okay. So initially there is an increase and then decrease. There is an increase and then decrease. Is it clear? And this is the optimum pressure ratio to get the maximum output for this temperature, for this T03, right? If I draw a tangent here like this, okay, so I can get what is the maximum pressure ratio. Suppose here, if I draw it, if it may come like this here between 10 and 12, maybe 11 for this. For 1300 Kelvin, the optimum pressure ratio may be 11. Am I clear what I am talking?
Yes, sir.
Okay, in the same way, if I see how it is changing with the turbine inlet temperature. As turbine inlet temperature increase, what is happening to SFC? There is a small decrease. Am I right? SFC is decreasing a little bit because efficiency will increase. But output, there is a large increase in the output. Because turbine inlet temperature is increasing, large output will be there. But increase in the efficiency is small and decrease in the SFC is also small. Am I clear? Why? Because the output increases and also input increases. Turbine inlet temperature increase means input also increase. Both output and input increase. The net effect is a small increase in the efficiency or decrease in SFC. Is the argument clear about this graphs?
Yes, sir.
Okay, so these graphs are very, very important. Why? Because if somebody wants to design a gas turbine, okay, so what are the main specifications? Like if somebody asks or somebody wants to buy some a gas turbine power plant or establish, so what are the main things he need? He needs efficiency and output. Am I right? So once you know efficiency and output, efficiency means SFC. So if I know SFC and output, it comes to a particular combination of turbine inlet temperature and pressure ratio. That decides what is the pressure ratio I need for the plant and what is the turbine inlet temperature I need for the plant. Once I know that, I can draw the complete figure, the thermodynamic analysis I can do, right? What are the things I need for thermodynamic analysis? I need pressure ratio and T03 because T01, P01 are fixed from the ambient conditions. So for cycle analysis, what I need is T03 and pressure ratio. Am I right or not?
Yes, sir.
So based on the application, I have to be clear about what SFC I need and what output I need. Once SFC and output are decided, then I can have the performance curves. These are standard performance curves. And I can decide what is the pressure ratio and T0 that gives me the required output and the efficiency. And once I know that, I can do the thermodynamic analysis. Okay?
Yes, sir.
Okay. Now, if I go to heat exchange cycle, okay. So if I go in heat exchange cycle, what happens to, what is the effect of pressure ratio on efficiency and output? What is the effect of pressure ratio on efficiency?
Decreasing, sir.
As pressure increase, efficiency decrease. Am I right?
Yes, sir. Yes, sir.
And SFC increase. So we will see how the graphs will change, right? The graphs will be changed like this. So here, these are the constant pressure ratio lines, and these are the constant turbine inlet temperature lines. Okay, like this, I will have a family of curves. Now we will see as R increase 4, 6, 7, 8, 9, what happening to SFC?
Increases.
Increasing. Why? Because efficiency decreases. Am I clear? And again, for a given turbine inlet temperature, we know that there will be an optimum pressure ratio. That's why it increase and decrease. It increase and decrease. Is it clear? So this is also same. Now coming to turbine inlet temperature. So as turbine inlet temperature increase, naturally output increase. Right? Output increase. But efficiency increases because I am recovering the heat using heat exchanger, right? So the efficiencies are very high, and so the SFC will be very low. So as my turbine inlet temperature increase, my SFC decrease. So you can see the difference in the simple cycle in the heat exchange cycle. So whatever we have concluded, that I have to be clear from the performance characteristics. So here also I can decide if I want to have a heat exchanger for a given SFC and turbine output, the specific work output, what is the pressure ratio and temperature needed? And based on that, I have to design. Is it okay?
Yes, sir.
Yeah. And actually, this one more thing I want to show. Yeah, this one. Okay, this is taken from Cohen only, Cohen and others. So maybe I cannot see. Difficult to see here. Maybe in the textbook we'll see that. I want to show this design procedure. So like this is the design procedure for a flow chart, right? Typical gas turbine design procedure. So you can see so I have to get the specifications. So how to get the specifications? So I have to do market research and I have to see what are the customer requirements. And based on that, I have to decide what are the specifications. So once I under the specifications, what I told specifications are SFC and output. So from this, we have to do preliminary studies and we have to choose the cycle. And once I choose the cycle, Then I have to choose what are the types of turbo machinery I need and layout. And so thermodynamic design point studies. So I have to do the thermodynamic studies. Once I decide about the cycle, I have to do the thermodynamic studies. So after the thermodynamic studies, I decided pressure ratio and turbine inlet temperature. So pressure ratio tells me what type of compressor I need, how many stages of compressor are needed, whether it is centrifugal or axial, or if it is axial, how many stages I need. All these things will be decided based on the pressure ratio. Okay, so turbine inlet temperature decide what is the combustion chamber should be, how it should be to get that particular temperature. And after that, I have to do the aerodynamic studies. These are the things we are going to discuss in the whole syllabus. Aerodynamic studies of compressor, turbine, inlet, exhaust. So that is the inlet triangles, outlet triangles, what is the shape of the blade profile, and all those things we decide. Okay, so these studies we are doing in this subject. Okay, thermodynamic studies now presently we are doing the cycle studies and all, then aerodynamic studies, component by component. And then, so this we will not do, design people will do, mechanical design. That is stressing of discs, blades, casings, or stress calculations and all. Okay, so those things are made by design people. And once I do that, then detailed design and manufacture. And at every point, I have to go back and see if there is something it's not possible, or if I have to change material, if I have to change some things because something goes beyond the limit, something impractical like that. So every time I have to go back and modify the initial things. So this is the way I have to go about the design of a particular gas turbine power plant. So testing and development and the production, and then after sales service. Okay, so here after testing and development, if there is any design modifications I have to do, again detailed design and manufacture, and again testing and development. And or I may have to do component test tricks. So once I develop the components, each component is to be tested. Okay, after testing, again there may be modification, and I may have to again go for the from the design point study. So like that, there will be a lot of back propagations and forward propagations, and I have to complete this. Okay, this is the design method policy. Okay, so the next thing what I want to discuss is about combined cycle power plant. Okay, we will see the concept, and maybe if time permits, we will try to solve problems also for the combined cycle. Actually, this combined cycle, there are two things. In any power plant, there is whether it is power plant, industrial power plant, or aircraft power plant, there is what is called as base load and another peak load. Okay, if it is industry, suppose if it is aircraft, so cruising thrust and takeoff and landing thrust. Okay, so most of the time I have to have minimum base load, and sometimes there will be some time periods there will be peak load, just like traffic, right? The current load also, there will be sudden increase in the some during some hours. Am I right or not?
Yes, sir.
Okay, in the same way, if I take aircraft, so most of the time it will be cruising, going at constant speed. But during takeoff, during climb from lower altitude to higher altitude, or during landing, the thrust needed will be different. Okay, the main, I think we have already discussed, studied about the advantages of gas turbines over IC engines advantages over steam turbines, right? Like that, we have seen what are all the advantages with the gas turbines. These are very high speed, very high power to weight ratio, and efficiency also will be good. But what is the main disadvantage with gas turbine? Can anybody tell me why they are not used in automobiles?
Efficiency is low, sir.
Efficiency is good only, not compared. It is comparable with the IC engines. The main
Temperatures.
yes,
Temperature.
no. The main
Starting issues, sir.
it is efficiency only, but not just thermal efficiency. It is what is called as path load efficiency. Path load efficiency is very poor. Or off design performance is very poor. Okay, do you understand what I mean is? So we design it at some particular things for particular speed or thrust, and whenever the speeds are changing or the needed thrust is changing, the efficiency falls down very much. Okay, so automobile runs at different speeds. I don't run it at constant speed, right? So that's why the gas turbine is not will not give a good performance. But they are used in sports cars. You will get very good thrust, very high power to weight ratio, because most of the time it runs at high speed only. Am I clear?
Yes, sir.
In the same way, aircrafts, okay, 90% of the time or 95% of the time it goes at constant speed, cruising speed. Only during takeoff and landing, the speeds are different. So no problem. Only a small time it is used off design. That's why they are suitable for aircrafts, but not for automobiles. Am I clear? So, but when you come to industrial power plants, okay, base load most of the time, but peak load also will be a bit sufficient period will be there. So that is one of the main problem with that. So what we do is normally we go for what are called as combined power plants. So it is something like, okay, there are various configurations like COSAG, CODOG, COGOG, COGAG, COSAG. Like this, different configurations are there where CO is combined. Okay, S means steam, G means gas, D means diesel, O means R, A means and. Is it clear? So what is COSAG? Combined steam and gas, combined diesel or gas, combined gas or gas. Two gas turbine power plants will be there. So one for base load. Whenever peak load is there, the other one will be started. So combined gas and gas, combined steam or diesel, combined gas and steam. Like that, there are various configurations are there. These are combined power plants. Okay, so this is one concept I want to tell you. And there is another concept I want to tell is bleed. So what is this bleed? Have you heard about it?
Extracting the gas before it comes out of the turbine.
No.
So for brakes, we need to do bleeding so that there won't be any gas bubbles inside the brake fluid.
No. Actually, in steam power plants, if you have studied Rankine cycle and all, there is also bleeding is there. Have you studied about feed water heaters? in steam power plants. Feed water heaters, have you heard about it?
Yes, sir. To preheat you are using.
Preheat?
Preheat the water. Preheat the water.
Preheat the water using?
Steam from turbine, sir.
Yeah, steam
Feed
from.
water.
Yeah, during expansion, in between, we bleed some steam. Between stages, number of stages will be there. Between stages, I take some steam to heat the feed water. That is what is called as bleeding. Tapping steam to heat feed water. We use what is called as feed water heater. This tapping steam is called bleeding. Am I clear? This is in steam power plants, in steam turbines. And gas turbines, it is not that. Here, at as T03 increase, we need blade cooling and disk cooling. Disk means rotor disk or stator disk. So these are the things I need. I need to cool them. How to cool them? I have to use compressed air is used to be used. Okay, so bleed air after compression to cool them. Is it clear? After the compression, I take some air for cooling of the turbine blades, rotor blades, stator blades, and discs. That is called as bleeding. And so this is given as percentage. Okay, so it is something like beta S, beta R, beta D. Fraction of air for stator blade cooling. And beta R, fraction of air for rotor blade cooling. And beta D, fraction of air for disc cooling. Okay, so these are the things which will be bled out. So here what happens is, because later whatever is cooling the stator and disc, that will be combined with the combustion chamber gases, and it goes to the turbine. So if you see m dot A for combustion chamber is m dot A into 1 minus beta S minus beta R minus beta D. This is the mass flow going to the combustion chamber. Am I clear?
Yes, sir.
And m dot A for turbine will be equal to m dot A into 1 minus beta S minus beta D. Sorry, not that. Sorry. Beta S and beta D will be added, and 1 minus beta R only will be there. Whatever is cooling rotor, that only cannot be mixed with the mainstream. The stator and disk cooling air will join with the mainstream. So only this much will be there. And sometimes if you want better calculation, m dot F will be there. Is it clear?
Yes, sir.
Okay, this is the way it will be used. This is called bleeding. The next thing what I want to talk about is combined cycle power plants. So usually combined cycle power plants, though I told the Kodak, Kodag and all those things, the main things is co-gas, combined gas and steam power plant. Okay, there is something like what is called as cogeneration. Have you heard about cogeneration? Okay, so after the gas turbine, some exhaust is coming out, right? So this exhaust gas temperature, which is called as EGT, is very high. And suppose if I take the previous problems, okay, we'll see here what is the T0, T06. See what is the temperature here? How much it is? 1053, 1053.8 Kelvin. 1000 degree gases are going out just like that. So this can be utilized, right? So much of heat is there. Either you have to use a heat exchanger. Heat exchanger also only some of it can be used, and still lot of thing is lost. And it can be used for a better purpose also. So if the exhaust gas is used for some useful purpose, that is called as cogeneration. Am I clear?
Yes, sir.
Use of exhaust gases for some productive use. So there are various uses. Maybe I can show that. Yeah, cogeneration. So in a cogeneration plant, later there is a figure here. The steam generated in this is heat recovery steam generator. HRSG means heat recovery steam generator. So I can generate steam using the exhaust gases from the gas turbine. That is called as heat recovery steam generator. Okay, so generating of steam for recovering of heat from exhaust gases is used for several different purposes. So whatever steam that is generated, that can be used to run a steam turbine, and you can drive a centrifugal water chiller, a heat source for absorption chiller. So absorption, you know that vapor absorption refrigeration system, it needs some heat. So you can run the absorption chillers, and to meet process and heating requirements. In chemical industries, there will be process heating you need. And in paper industry, you need for drying paper or something. In many industries, you need high temperature steam, or some high temperatures are needed. Heat is utilized in various ways. So see, such as hospital or paper making factory, and different requirements for steam. And even though the same gas turbine may be suitable for a variety of cogeneration plant, HRSGs would be tailored to the specific requirement of the user. Okay, so heat recovery steam generator is used in various power plants. Okay, so combined cycle power plant is one method in cogeneration. Okay, so you can use the heat in any way. So all the ways are cogeneration, and one of the special case is combined cycle power plant. Is it clear? So there is one layout is given. There are various chiller power plants. Chiller plants are run like that. Okay, so that is about cogeneration, and we will see about combined cycle power plant. Okay, this is the way. And so suppose now So this is the Brayton cycle I have. And if I can use this, okay, this is the Rankine cycle. Sometimes we call this as a topping cycle. And this is bottoming cycle. And this is Brayton cycle. And this is Rankine cycle. And here, if I take this is HRSG. Okay. So what I will tell you again. And this, so exhaust gases from the turbine, it enters here. This is a heat exchanger and it comes out like this. And this is losing heat. And in opposite way, counterflow heat exchanger, it is HRSG. Heat recovery steam generator. This is counterflow heat exchanger. Okay. And so the steam, the water here gets heated up. It is coming in the opposite way. Then it gets evaporated and then it gets superheated. Okay. So this part is called as economizer. And this part is called as evaporator. And this part is called as superheater. Okay. So this is the way the heat is taken by the steam or water in the steam power. In Rankine cycle, this heat addition, whatever is there, is taken from the exhaust gases here. Am I clear about it? So gases enter at this temperature. I think I take it as not 4, and this comes out like stack. This is called stack temperature. What is going out of the chimney? And still this will be higher only, but it has to go out. We have to lose QL will be there, isn't it? So that will be lost. And so you can take here. So this from here to here, the steam water takes the steam. This is the heat lost by gases. This is heat gained by the water. And still, okay, if you take the area under this, that is heat lost by exhaust gases, and the area under this line, okay, so that is heat gained by the steam, and this heat is lost. Am I right or not? The area under this line is heat lost by exhaust gases. The area under this is heat gained by the water, and this is lost. And so I have to keep these two lines as close as possible to make the heat lost minimum. Am I clear?
Yes, sir.
Yeah.
Yes.
Yeah. And this difference in the temperature, okay, this is what is called as pinch point difference. Okay, so this should be as less as possible, but it should not be too less also. If too less, what happens? If it is too high, the difference is too high, we lose heat. If the difference is too less, heat transfer will be very slow. Am I right or not? If difference in temperature is less, the rate of heat transfer will be very, very small, and I have to have very large heat exchanger. Am I clear about it?
Yes, sir.
And in the same way, this is called as terminal temperature difference. terminal temperature difference. This also, right? It should be as minimum as possible. But minimum value is 20 degrees. Minimum 20 degrees difference should be there to have heat transfer. It should, if it is more, we lose heat. If it is less, cost will be high. Okay, so here the trade-off is between efficiency and cost. Right? If you want to recover heat, the heat exchangers will be large and it will be costlier. And if you want to make it cheaper, so the temperature difference should be more, it will be compact, and but we lose the efficiency. Okay, so that is the thing. Am I clear about this discussion?
Yes, sir.
Okay. So this is so usually sometimes this may be a gas turbine cycle. If you want to have a closed cycle gas turbine, you can have helium. Okay, so like this is the topping cycle. This is the bottoming cycle, which is the Rankine cycle. And here for this cycle, combustion chamber, gas turbine, and heat exchanger. Sorry, this is cooler or a heat exchanger. Okay, this process is heat recovery steam generator, and this is also called sometimes as WHRB, HRSG, or waste heat recovery boiler. Okay, this is also another name for it. So different books use different names. Waste heat recovery boiler. Okay, so this is the cycle, and so whatever heat is given by this, okay, this is Q2. Okay, it is lost, but out of Q2, something will be lost and something only will be taken. Q3 is the heat taken, and QL is the heat lost. And here it takes Q3, and here also there will be some heat that will be lost. Okay, so here there will be some heat lost between these two, and from here there will be some heat lost. It's not Q3 actually. This is Q2, and Q3 will be from there only. This is Q3 and this is Q4. Is it okay? And so if I do some calculations, you can see that the heat lost by exhaust gas is mgCpg into T4 minus this is T stack. Okay, this is the heat lost, and heat gained by the steam is ms into H minus HF. H is the exit enthalpy, and this is HF, that is it is entering as fluid, right? So it is that is a liquid, so it will be HF, and this is the enthalpy of the fluid. So actually this decides how much steam is to be supplied, how much steam can be generated. So because all these are known and this is the one which is not known, so like that I can calculate. So mgCpg into, okay, this is the one. And so the total efficiency is work developed by gas turbine plus work developed by steam turbine by Q. This is the input, and this total will be there. And the efficiency comes more than 50% if you have combined cycle. And all the present NTPC power plant, National Thermal Power Corporation power plants, all the recent power plants are combined cycle power plants only. Is it clear now? Because coal is getting depleted and we are getting gas, more gas. So gas turbine is used and the exhaust is used to develop the steam. And what is the maximum temperature in steam turbine? You know, anybody?
1800 Kelvin, sir.
No. Steam turbine. Gas turbine itself is only 1200 to 1500. 1500 is the maximum now we are using. 1350. You can see the problems 1350. I mean, it is less than 1500 only always. Gas
50,
turbine.
sir.
Steam turbine, if it is more than, it is so high, then I cannot use the gas turbine exhaust gases to produce steam. And how much? Somebody is telling some number? Approximately.
Steam.
It is some 550 to 600. Maximum turbine temperatures, steam turbine temperatures are 550 to 600 degrees centigrade. Is it clear?
Yes, sir.
Yeah. Okay, that's why I use them. And why the steam turbine temperatures are limited to somewhat less temperature than gas turbine temperature? Can anybody guess something? I told you gas turbine, it can withstand up to 1500. But steam turbines, they can withstand only 550 to 600 degrees centigrade.
Sir, is it by wear and tear of the water droplets?
Normally, we try to see that it won't get condensed during expansion. Actually, that is one of the main condition. So when I'm doing like this, and that's why superheat also is needed. So here, this that is wetness should not be greater than 5%. That is it. Just at the end, it may a little bit condense. That is allowed because it is fast. It doesn't matter. So that much only is allowed. Otherwise, as you told, there will be a lot of wear and tear will be there. If condensation starts, bubble forms and the bubbles hits and it will get eroded. So if you see the range of pressures, right? So we have seen in the problems, right? Maybe 4 bar, 12 bar, like that. Maximum, it may come to some 12 to 15 bar. Okay, but in steam turbines, anybody guess? There are what are called as subcritical boilers and supercritical boilers. Subcritical boilers up to 120 bar. It's very common to go like that. And supercritical, it goes nearly 230 bars. Supercritical, that is, it goes above like this. Okay, like Benson boiler. Okay, which is supercritical boiler. So the pressures are very, very high. So high pressures and temperatures. So this leads to what are called as creeping stress. Okay, large creeping stress. That limits the temperature to 550 to 600 degrees centigrade in steam turbines. Is it clear?
Yes, sir.
Okay, so, and another thing is, as T4 or T04 increase, steam pressure can be increased. Because in the things I have shown, so if this T4 goes up, and this line also can go up, I can increase the steam pressure. Am I right?
Yes, sir.
Yeah. So by increasing the boiler pressure, I can increase the efficiency. Efficiency of steam turbine increase. Okay. So I need not worry that there is a lot of pressure. The more high the temperature at the exit, so the more will be the turbine efficiency. If there is no steam turbine, I am losing more heat here. So now I need not worry. Even if I have reheat, it is more better. Reheating will increase the exhaust temperature further up. So I can go for high steam pressures and I can increase the steam turbine efficiency. Am I clear? And sometimes there is what is called as dual pressure system. So dual pressure system is something like this. I can show you. This is single pressure. Okay. So dual pressure, I can have 2 cycles like this. So it is something like this. So here, this is again, this is one cycle, this is another cycle. There are 2 steam cycles. One is high pressure cycle and another low pressure cycle. And this 4, 5, 6, this one, right, for the low pressure, and this goes in this way. This is economizer, evaporator, superheater for the low pressure cycle. And for high pressure cycle, this is like this, and this goes this way. So that the heat lost, you can see that these lines are going near to the exhaust gas line. So the heat lost can be reduced. Am I clear about it? Is it clear?
Yes, sir.
So if I have dual pressure system, I can reduce the heat loss. Okay, this is LP economizer, LP evaporator, HP economizer, HP evaporator, HP superheater, like that. I can make it more near to this. If I have single pressure, it goes like this. Okay. And here some calculation is given. If the thermal efficiency of the gas turbine is 34% and steam turbine is 32%, and if these temperatures, okay, this small formula, it is simple, you can just go through it. And so if those temperatures are given, you can have 51.3%. Normally for gas turbines, it will be around 30% only. For steam turbines also around 30%, like 0.34, 0.32, like that. Even IC engines also will be around that. But if I have combined cycle power plant, I can have efficiency more than 50%. And if I have more complex steam cycle, like dual pressure steam cycle, like that, it will be steam turbine efficiency will be up to 0.36. Then the overall efficiency come to 53.5%. Okay, which is typical of modern combined cycles. Now present day combined cycle power plants can have this much efficiency. It's so high actually. Okay, so that is the advantage of it. Okay, and the small things, one more thing, closed cycle gas turbine. So a closed cycle gas turbine will be like this. So here, okay, this is the compressor, intercooler, HP compressor, and then this is heat exchanger. After compression, it is heated by exhaust gases. Okay, so this is heat exchanger. Then this is the combustion chamber or gas heater. It is because it is closed cycle, combustion will not be there. The composition will not change. There will be only heater. This is external source heat. As I told, it can be nuclear power plant or it can be solar energy or whatever it is. It is heating this gas. And this is expanded in the turbine. And this turbine exit, it goes to the heat exchanger, right? And it is to be recirculated. So I have to cool it. Am I clear? Joule cycle, there should be heater and cooler because it is to be recirculated. I am not leaving it to the atmosphere. Am I clear about it?
Yes, sir.
Yes, sir.
Yes, sir.
And but after some cycles, what happens is there will be some leakages will be there. Some things will be lost. Even in the steam cycle also, I tell it is closed cycle power plant, and whatever water that goes and it becomes steam and it again condensed. And but we will lose some of the water during steam and during leakages. So there will be some makeup water I have to add always. For every cycle, there will be some loss of working fluid will be there, which is to be added. In the same way, here also some air may be lost, working fluid may be lost. So there will be some LP reservoir and HP reservoir. I have to supply the last whatever it is. This is called makeup. So this is closed cycle gas turbine. Is it okay? This is the way it works. Okay, I stop here. But as I told you, have to solve the problems. You have to work out the problems. And I will give you a worksheet also as an assignment so that you will have practice. And with this, I stop the gas turbine practical cycles. Next class, we will go to propulsion, aircraft propulsion cycles. And actually, whatever I have done, most of it you know a little bit in your BTech. Okay, so we have some additions here and there. That's all. So there is nothing much to worry. I think you have solved gas turbine cycles. Brayton cycle you have solved it, isn't it? Because whatever I have taught here, I teach BTech people also in turbo machines. So second turbo machines subject is there. There I teach all this. And they also solve the problems. Okay, so I expect you to be more smart and quick. So try, practice. Okay, shall we go for the story then?
Yes, sir.
Okay, I didn't have the story here. Okay, I'll go for one story. Okay, then I will tell a story. I will tell a butterfly story. Okay, so there is one boy who is very much interested in observing the nature. All scientists come because of their love of nature. Okay, they try to find out the secrets of nature and they become scientists. Okay, so all science is in the nature. So he is very much interested. He observes always what happens in nature and all. So one thing he gets attracted is butterfly. Such beautiful butterfly, and he wanted to see how it comes. Okay, so you know that there will be eggs. They form caterpillar, and then they construct cocoon, and then come butterfly. And he really got surprised. The caterpillar, it is so horrible to look at, and he get irritated to see that. But a butterfly comes out of that, such a beautiful butterfly. So he wanted to see what exactly happens. So he started observing the caterpillar, and it eats the leaves and those things and all, and he starts observing. And then at fine day, he starts constructing its own cocoon. And finally, the cocoon is made and it is trapped inside. Okay, he started observing when it comes out like that. And it needs a lot of patience. So finding out or inventing something or discovering something, it needs a lot of patience. And so he started observing and all. And some fine day, he started seeing a small crack that appeared on the cocoon. So he got thrilled. Okay, so he's excited to see how it comes out, how it comes out like that. And slowly it started increasing like that. The slit that is happened. Okay, that crack is started increasing. And after some time, he didn't see further increase in the crack. So he's worried. Maybe that fellow inside is not having sufficient strength to open it and come out. Okay, so he was worried actually. So he wanted to help it. So what he has done is he has got a small scissor and he has a little bit cut it open. And immediately that fellow inside, he pushed it open and just fallen down. And it is not completely grown. It is just limping like that. Okay, his wings are not open. And because he heard from science and all, there will be some premature babies in the humans also. Maybe this is a premature baby, and gradually it will develop and it will open its wings and fly. And he started observing, but unfortunately, it never could fly. And he didn't understand why it is not growing, why it's not flying. So then he went to his science teacher and asked him, teacher, what happened like this? I wanted to see it fly, but it's not flying. Then he asked what happened and all, and he explained everything. And the teacher said, so see, because of your love and concern, you have harmed it. Because it has to open it by itself. Though it is struggle, it has to struggle. While struggling, while trying to put the body inside the crack, what happens is the fluid in the body gets pressed. So when it gets pressed, it tries to flow, the fluid flows into the wings and it gets life into the wings. And then it can fly. But because of your love and concern, you didn't allow it to happen. So the fluid is in the body only. So it didn't go into the wings. So that's why it could not fly. And it says, that's why the struggles in the life you have to face. These are designed by the God to make you develop. And don't get help from somebody so that life will be easier. So your life will be easier, but you will be like a disabled person. Okay, always, that's why I always repeatedly say the sufferings and tests and adversities, everything in our life is designed and it is for our own development. We have to welcome it. We have to be happy about it because it is for our own development. Okay, thank you. Thank you very much. See you in the next class. And so most probably 99% we will have test on Monday at 6 o'clock evening. I will load it in LMS if it is ready.
Sir, for some students, we have class from 5:15 to 6:15 HEV, sir.
Okay, maybe 6:30 then. Okay.
Okay,
6:30 or 7 if you want, I can have it 7. But it
Okay,
doesn't
7
matter. 7 o'clock, right?
Yes.
It will be short period only. Okay.
Okay, sir.
Anything else you would like to ask?
Up to this class, sir.
Yeah, up to this class.
Objective type.
Objective type, MCQs.
Okay, sir.
Okay. And I will give you some problem sheet I will try to give so that it will be there for you. And all minors will be MCQs and mid and final will be only problems and derivations if they are. Okay.
Okay, sir. Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Yeah. Any difficulty, anything